So basically for file 1, this is what we're discussing. Oh yeah, and then I have to apologize firsthand because the PowerPoint is in Indonesian. I haven't translated them to English yet. So I think, yeah, you should understand, hopefully. I'm sorry about this. So basically ini yang pertama, sistem persamaan linear. I won't stay very long here because we have lots to discuss. So basically, this is the one of the core parts of linear algebra. This is one of the core parts of linear algebra because you will use this in all the other chapters that you will study. So basically, you have two types of let's say you're given a matrix percent and then you're asked to convert it into into two different basic forms. The first basic form would be what we call row echelon form, and the second one is called reduced row echelon form. So basically here, this is ini namanya row echelon form. Ini reduced row echelon form. So the difference between these two is the content of the matrix and the shape of the leading one. So basically, for to determine whether a matrix is in its row echelon form or in its echelon form, would be to determine the leading one. Now, what is the leading one? The values here. These are called leading ones. So for the difference is that for reduced row echelon form, the leading one must stand alone, quote unquote stand alone. What do I mean by that? So since this one is in reduced row echelon form, when I say the leading ones must stand on its own or diri sendiri here, take a look at this one. That's the second one. Do you see anything above and below it? No, right? It's just zero. So that's one of the easiest way to determine whether a matrix is in its row echelon form or reduced row echelon form. For reduced echelon form, if you look at the ones, the ones that has the column, there's nothing below the one value and there's nothing above it, just values of zero. And this applies to all. So basically, in all cases, the leading one in the next column must be one level below the previous column, just like this one. So basically, it must look like a stairs. Mas harus kelihatan kayak tangga gitu. So this is what we call row echelon form, the second set. So as you can see, let's say this one, the second one. There's one here. There's nothing below it, and there's four on top, just like this one and this one. Yep. So just basically just look at the numbers below and on top. So does it have other numbers aside from zero? So that's the easiest way to do it. Okay, so next. Okay, so basically, next we're going to study about elimination. So what is elimination? So let's say you're given a matrix. You are asked to convert to reduce echelon form or just a regular echelon form. There are two methods to use, which is the Gaussian elimination and the Gauss-Jordan elimination. So basically, Gaussian is for matrix to echelon form, and Gauss-Jordan is for matrix to reduced row echelon form. Yep. And when do you usually apply this? You apply this to find the solution to a system of linear equations. So basically, when you are dealing with linear equations, you will have there are three types of solutions that you can get. The first one is that the system has what we call a unique solution, meaning every variable only has one value. So for example, x is equal to 1, y equals to 2, z equals to 0, or something like that. And the second type is that the system has infinite number of solutions, which means, let's say x equals to 1, y equals to 2, but z equals to t, where t is an element of R, meaning t can be any number, to put it simply. This is called infinite solutions. Now, for no solutions, the third type, which is the third type, it means your system is inconsistent. So if I were to put it in matrix form, it will look something like this. It will look similar to this. Sorry, wait. There. This is called no solution system, because there's nothing here and the value is equal to, and there's the value of 2 here. This might seem a bit abstract to you, but then if you go through the notes that I give in the drive, it will somehow make sense to you. Okay, so this is an example from the book. This is I'm pretty sure this is the book that you guys use, the one by Howard Anton. If you want, I can upload the PDF after this. Okay. And next, this is an example on how you do the elimination. This is just an example. So basically, from this to this, the first thing that you should do, I forgot to mention, how do you find the solution? The first thing that you should do is to convert the system into an augmented matrix system. What do I mean by that? If you look at the next slide, this is called an augmented matrix system. This one. This one is called an augmented matrix system. Basically, you transform this into this form. Now, the separator here is for the values here, the one opposite the equal sign. So basically, what you should, after you convert it to this form, then you perform the Gauss-Jordan elimination. From this, you can get something like this. And this is an example of a system that has infinite solutions. The bottom row are all zeros. So what do we do with that? We just take note. If you can see here, the value, there are 6 variables, right? From x1 to x6. Now we take a look which one has leading ones. And we see that x6, x6, x3, and x1 has leading ones. This one, and this one. So that means x2, x4, and x5 does not have leading ones, meaning we can directly assume that they are with this thing called parameters, which are T, S, and R. You can use any letters you want. You don't have to use T, S, and R. Okay. If you want to understand more about this process, you can just look at the book and find this example. Okay. So this is a linear equation for a system that does not have a solution and only one solution. As mentioned previously, this one has no solution because the last row is inconsistent. This one, the last row. And a common trait of a system that has a solution is the number of equations and the variables are the same. So let's say we have three variables, x, y, and z. That means we must have three completely different equations. And the next one is that the next criteria is that the first let's say we have a system of equations. The first equation must not be a multiple of the second one. What do I mean by that? Take a look at this one. Let's say we have two equations, 3x plus 4y equals 6 and 6x plus 8y equals 12. If we were to multiply the entire row, if we were to multiply the first equation by 2, we will get the second equation. So if we see this straight, then automatically we can somehow determine that the system has infinite number of solutions. Okay. Next. Okay, so let's say we have a system of linear equations. There are actually multiple ways to solve it. The next two methods are the methods that require finding the determinant. The first and second one, the first method is called the Cramer's method. And this is actually a segue into the second one, into the second chapter. Because the second chapter is about finding the determinant of the matrix. So basically, for a matrix to have a determinant, it needs to be a square matrix or an n times n. So basically, we'll start with the Cramer's rule. For Cramer's rule, let's say we have we have a system that is like this. The first thing that we should do is convert it to a matrix format like this. This is called the coefficient matrix. This is called if I'm not mistaken, this is called the solution matrix, or yeah. And this is XYZ, the one that we're trying to find. So in order to find the value of X, Y, and Z, we first have to find the determinant of A, and this is A, the coefficient matrix, and also the determinants, determinants of AX, AY, and AZ. What is AX, AY, and AZ? AX is basically just matrix A, this one. This is matrix A. Basically matrix A. However, we put it in the position of X, Y, and Z. The position of UOP in X, Y, and Z. So if you look at AX, the X column, it's not ADG, but rather UOP, which is our solution matrix. Okay. And then, yeah, you get the value. The next one, this is a method I think that you have seen in your high school, I think, which is called the inverse matrix method, where basically, after converting the system into this form, we find the inverse of the A matrix, and then we multiply the A matrix with the B matrix, with the matrix B, or the solution one. And also, please note that A inverse B is not the same as B times A inverse. So be careful. So this is just a quick message to you when you're doing linear algebra. Just be careful what you're multiplying, because the values, because if you do this instead of this, or the other way around, you might end up with the wrong solution. Okay, I'll just box this. Okay. One zero 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 100. And how to find the inverse matrix method? This is a quick way on how to find the inverse. So basically, let's say you have this matrix A and you want to find the inverse. What you have to do is just make an augmented matrix like this, where on one side it is the matrix A, and the other side is the identity matrix. This is called the identity matrix. And then you perform Gauss-Jordan until the right side here becomes an identity matrix. And once you've done that, the left side will be this one, the inverse. Or you can do the difficult way of using this famous formula. However, this is only I would say this is only suitable if you have 2 times 2 matrix recommended. If your n, let's say, it's greater than 2, it's not recommended because it will become more difficult. This is always the recommended method to find the inverse. Okay. I think I should give you one more thing. Say, oh yeah. How do you convert the matrix into this form, into the row echelon form? Is by doing row operations. What are you allowed to do for row operations? You are allowed to switch rows. Do not switch columns. It is not allowed. And the next thing you can do is multiply any row by a constant. And the third thing that you can do is performing how do I say this? Perform calculate, not calculate. Uh, perform addition or subtraction in between, subtraction between each rows. I think you should know this by now. So what I mean by each of them is this. So what I mean is For this one, so basically for this one, sorry, slight difficulties. So basically for this one, this is the symbol. What happens is, let's say we have A, B, C, D. If we were to do R1 to R2, it would be C, D, A, B. Now for this one, multiply a row by a constant. It's just KR1. So basically what happens is, let's try this time R2. KR2. We're doing this A, B, KC, KD. Now for this one, you can do R1 plus KR2 or R2 minus KR1, where and this part here is called the pivot rows. And it will remain unchanged in the operation. So let's say ABCD, and let's say we want to do R1 minus KR2. So what happens is, we take a look at the first row, A, and the second row, C. So we minus it by A minus KC. This is B minus, we do the same thing for the second column, B minus KD. And R2 remains unchanged, CD. Okay, so I forgot to tell you this, so I think you should know about this. This is very important. Okay, so that's it for a chapter 1 speed run. So basically the next part is the to find the matrix determinant. So what do I do with this chapter? So the first one is what you can do with determinants. The first one, let's say you have a matrix A, and this matrix A is multiplied by a constant. So basically, in order to find that new matrix, the determinant of the new matrix, it will be that constant times the determinant of A. So if we let's say we multiply two matrices together, A and B. To find the determinant of the new matrix, it will be the determinant of A times the determinant of B. So and the next one, if we transpose matrix A, the determinant doesn't change, it will remain different. And what do I mean by transpose? Let's say I have this. A, B, C, E, E, F, G, H, I. If I were to transpose this, it will become, the row will become the column. So this is ADG as a row. So now this becomes a column. Same goes for the next one. Okay. And next, if we have to find the inverse, the determinant of the inverse, the determinant of A inverse is just the reciprocal of the determinant of A. And in order to save time, you can take a look at this by yourself. What happens if we have a triangular matrix? And what happens if we have a diagonal matrix? Oh, and ignore this one. Yeah, I'll just erase this. Okay, so next. So basically, these are the types of matrices that have a determinant equal to 0. So you can go and have a look, and you can go try it by yourself. Why? As a challenge. Okay, so how do we find the determinant itself? So there are actually 3 different methods that you can use. The first one would be cofactor expansion. So the first thing that you should do is to identify your matrix, and then if you're still confused, assign a plus and minus to each of the cell. So let's say we have a 3 times 3 matrix like this. So the first thing that you do is assign a plus and minus. They should interchange. What is this for? Is to be used for cofactor expansion. The important part. Now for cofactor expansion, you can do it based on the column or based on the row. So what do I mean by the column? So let's say we use column 1. So this is the column 1. This column automatically becomes the viewpoint. And then we do it based on the values of each of the rows. So what we do is, let's say for the first component, where do I get 5, 6, 8, 9? If to help you, draw a box here. And this is the value that you get, 5, 6, 8, 9, because it's the first row. Let me erase that. Now, the same goes for the next one. How do I get 2, 3, 8, 9? Just cover the second row. You see? 2, 3, 8, 9, and so on. Now, how do I determine this, the sign? From this, the plus minus matrix. So since we're doing it based on column 1, so this is what we're using. Okay. And next is based on the row. So let's say this time we use row 2, which is this one. So which one do we use for row 2? This one. The same process applies here. So how do I get 2, 3, 8, 9? Just draw a box with the first row. So you see 2, 3, 8, 9. For this one, for the same goes for the second part, just draw a box in the middle. It's 1, 3, 7, 9. So this is 1, 3, 7, and 9, and so on. And so you get the determinant if you calculate. Oh yeah, guys, before I forget, if you look at the bracket sign to find the determinant, it's different. Make sure that you do not interchange these two, yeah? Between this and these, they are not the same. Do not interchange the two, or else you might get penalized for it. The second one, to find the determinant, the second one is to use elementary row operations. So the first thing that we should do is to understand what does row operations do to the matrix. So if you were to do row reductions, that's what I was thinking, row reductions, nothing will happen. So this is the for this to become this is the operation that we do. So if you take a look, nothing happens. Nothing will happen. However, if you were to multiply with a scalar, let's say this is the scalar here is -1. Sorry, this is not multiplication by a scalar. This is if we switch rows. Every time we switch row, the determinant will be multiplied by -1. And the next one, if you were to multiply a row by a constant, that means the determinant will be also multiplied by that constant. As applied, yep, this is what happens. So the first, how do I do this? So let's say I have A, B, C, D, E, F, G, H, I. I need to convert this into a triangular matrix. So this is, let's say, A, B, C. This is 0, 0. This is D, E, 0, F. This is called a triangular matrix, just like the one here. This one. After I got that form, I can simply calculate the determinant, and the determinant is A D times D times F ini ya. Okay, so the last method is a mixture of method 1 and method 2. So this is the strategy that you use. So the first step would be to use method 2 to make some of the components gone. So what I mean by that is that, let's say we focus on the first row to make it easy for us. We knock out 4 and we knock out 7 using elementary row operations until we get 1, 0, 0, 2, 3, A, B, C, D. And the next thing that you should do is perform cofactor expansion. And if you look at based on the first column, this one, if you were to observe, the resulting determinant would be just this one, A, B, C, D. And then you can just do the usual calculation. Okay. As you might have noticed a bit, there are not a lot of examples here, and the plan is to just go through the materials quickly, and then if we have time, discuss some materials. However, should there be not enough time, the plan, I already upload some learning videos in the drive that has been given to you, so you can study from there as well, which I hope would be sufficient. Okay. And the third one after this is the third chapter, which is Euclidean vector spaces. This is a bit of a tricky chapter, and so since just a bit tricky. So because yeah, it can get a bit abstract. There's a lot to digest. Yep. So this chapter 3 relies on chapter 2 and chapter 1. So hopefully, if you have the time, you can study it. Just study chapter 1 and chapter 2 so that you can master chapter 3 and the following chapters. From all of the chapters given, chapter 1 is the most important because you will use it until the end of the course. Okay. Okay, so the first thing is that we're going to learn is what is a vector. So basically, a vector here is something that has direction and magnitude at the same time. So which is why signs, meaning plus or minus, is very important, as shown on the image below. I think I need to close. So basically here, if you were to take a look, let's say this is the initial one, V, a vector V. Let's say we have a new vector A, and that vector is multiplied by a constant K V. If K, let's say absolute value K is, sorry, that was absolute value. Let's just say it's just if K is between 0 and 1, vector becomes shorter. As you can see here, it becomes shorter. If K is greater than 1, vector becomes longer, as seen here. And if K is negative, vector changes direction. Jangan pakai ini. Okay, let me just fix it because you cannot see the color. This one, so we have I will use dark blue. So that means this one becomes shorter, this one longer, this one travels opposite direction. I don't think travels is the right word, but yeah, it's okay. Now, this is just the first term vector. The next one is what we call bidang or plane. So what is a plane? A plane is a combination of barrels that are parallel to each other. Okay, so basically this is what a plane looks like. And the plane consists of many different vectors that are parallel to each other. And a vector can also consist of two different dots or points on a plane. So let's say we have an xy plane, and we have here V, which is x1 comma y1, and U, which is x2 comma y2. I can connect these two lines together, these 2 points together with a line, and this line can become a vector. And that vector is depends on the direction. So let's say v to u, it will be x2 minus x1 and y2 minus y1. This is the vector. This is the vector. It can also work for 3 dimensions like this, and also 2 dimensions as shown previously. Now a vector can also have a length, and this is the formula of the length. And the same formula applies to 2 dimensions. Now the next part is the property of perpendicular, tegak lurus, or parallel. If 2 vectors are perpendicular to each other, let's say we have vectors A and B, the dot product of the vectors would be equivalent to 0. If it's parallel, then that means A must be equal to KB. And it must apply to all vector components. If it applies to only, let's say you have a vector with 3 cells. The multiplication of K only applies to the first 2, but it doesn't apply to the third. That means that those 2 vectors are not parallel to each other. Okay. Okay, so next we have vector operations. So what happens if we multiply 2 different vectors? Sorry, not multiply, but if we add or subtract 2 different vectors. So this is the resulting vector called the resultant vector. If we add, this is what will happen. If we subtract, this is what will result. Okay. And there's another concept I would like to tell you is this thing called the unit vector. So basically a unit vector is a vector where the length is equivalent to 1. And so to find the unit vector will be the vector itself multiplied by the vector itself divided by its own length. There. And okay, what's next? This is what's called dot product. So the dot product of a vector would be the same as performing matrix multiplication on the vectors, in which one of them is the transpose. So basically, this is what happens. So let's say I have vectors u and v, and u is u1, u2, v is u3, u4. U transpose will be u1, u2. So basically, it will result in u1 times u2 times u3 and u4. If we multiply these two, it will lead to u1, u3 plus u2 times u4. So this is what happens. So this is the resulting calculations. Or in order to make it easy for you, I can just write U1, U2, U3, U4, and just draw arrows like that. So it's U1, U3, U2, U4, just to make it simple. And the next formula that you know is to find the angle between two vectors that intersect each other. So basically, to get this angle theta, you have to find the dot product of the two vectors divided by the product of the length of each of the vectors. And also bear in mind that this applies where the angle theta must be between 0 and 180 degrees, or 0 between pi radian. And if you forget the conversion, just remember pi radian equals to 180 degrees. Okay. If two vectors, as mentioned previously, are perpendicular, which means the theta is equal to 90, that means u dot v equals 0. Because if cos theta is equal to 0, the theta will be 90 degrees. Okay. And the next thing that we should do is what we call the orthogonal projection. There are two types. If you look at this diagram here, you will see two new vectors, W2 and W1. So basically, let's say we have two vectors, one a vector U and a vector A. W1 is the orthogonal projection of U towards A. So that means W1 has the same direction as A. So what the idea is, we want to make this have the same direction as A, or we can write W1 is parallel to A, and W2 is perpendicular to A. So this is how you find the W1 and W2. Okay. And if you notice, U, W2, and W1, they have this relationship. This one, the additional relationship, where in this case, U is equal to W1 plus W2. Which is why this is how we calculate W2. Okay. Okay, so I think that should be it. Next. Okay, these are just some properties of dot product. So basically, if you take a look, if we if you do dot product on the same vector, it will result in a square. And I don't think in the square of the length. And this is also important to note. And I think that you can have a look at it for yourself. This is another important multiplication, which is cross product. As now we have dot product, now we have cross product. Okay, now, okay. So bear in mind that cross product only applies to three-dimensional matrices. three-dimensional vectors. And let's say we have these two vectors, u and v. In order to find the cross product of u times v, we put u and v in this order. And bear in mind, guys, the order is important because of this property. And if you try compare, flipping it upside down, the result will be completely different. So make sure you put u and v in the right place. And this is also an additional formula to find the length. The length of u times v is basically of u cross v is basically the length of u times length of v times the sine of the angle between them. Like that. And where do you apply it? Is to find the area. So basically, if u and v are connected together like this, they actually can form a parallelogram or jajar genjang. If I draw two lines like this. In order to find the area, it is the length of u cross v. However, if we only find the area of the triangle, it is just half times the area of the perpendicular of the parallelogram. And also applies to okay, it applies to two-dimensional. If you, let's say we want to find a triangle on a two-dimensional plane, we just use this. Because as mentioned previously, cross product only applies in 3 dimensions. Okay, so these are the relationships for cross product. If you want to challenge yourself, you can try prove the Lagrange identity there. If you want to challenge yourself, right? Okay, so next is what if we apply both types of products together, a dot product and a cross product. So this is the resulting, this is what it should look like. So let's say we have t dot u cross v. Oh yeah, before I forget, so let's say you have two vectors. Let's say you do dot on u and v, you will get a scalar or a constant. If you cross, you will get a, not a matrix, but you will get a vector. So basically, since t is also a vector and u cross v is a vector, and since we are multiplying a vector dot product with another vector, so do not surprise you that it will get, that we were going to get a scalar. And as usual, the ordering matters. If you look at t, this is the first component, it goes in the first row. The following component is the u, it goes in the second row, v goes into the third row. So basically, we're replacing I, j, k with t. And where do you use it? To find the volume of this structure here, which is called a parallelopipe or something like that. I don't know the whether this is the correct term. Where T, U, and V are the sides of the parallelopipe here. The next application is another important one, which is to determine whether three vectors are on the same plane. Wait. Because if we were to take a look at this, let's say this is a plane P. A plane, as mentioned previously, consists of vectors. The idea of using U cross V is to show that it is inside here. And to show that T dot U cross V equals to 0 shows me sebentar. Okay. Okay. I got confused there for a second. So let's say this is U and this is V. This is the result, U cross V. If we can show that T is in the same plane as U and V, let's say T is here, that means T would have to be perpendicular to U and V. That means T would have to be perpendicular to U cross V. So which is why if we do this, we use this idea of dot product, that means T times U cross V must be equivalent to 0. Just remember this. Okay, so next is finding a line equation. So basically, there are many types of cases that you can get in your exam. But the general ones are you are given 2 points on the line. And the second choice, you are given the directional vector of the line. So let's say this is the line. This V is called the directional vector. And also a point that goes on the line. You will see it in the next slide, which is the example. And there are 3 types of equations that you can find called the Cartesian form, which is this one, your famous y equals mx plus c. Or a parametric equation where we express x, y, and z as parameters, whether it can be t, mu, lambda, or any other variable. And finally, a vector equation where we express it in terms of I, j, k, or this is, I can just write x, y, z. So next, this is an example. So find a line that follows through the point OA and OB, the first thing that you should do is to find the directional vector, which is OB minus OA. So this is what you get. So we can apply the line equation. This is the general line equation that we're going to get. This is general. So basically, we can change this into vector form by grouping each component that goes in the x, y, and z direction, or ijk direction. We can find it in parametric form by expressing each component. Let's say this one, this is x, y, z, this is x, y, z. And expressing it in this is the parametric form. And finally, the Cartesian form, which looks like this. How do we convert it? We just take a look at the parametric form, take a look at the t values, make x, y, and z in terms of t, and this is what you get. Then this is case 1, this is case 2. So the case 2, you are given a point and a directional vector. This is the simplest one because this will be your general equation. Where the directional vector is multiplied by a t, and r equals to 1, 2, 3. Okay, so the last part is the equation of a plane. So basically, would be the equation of a plane. As mentioned before, a plane is a collection of vectors that are parallel to each other. And this is the general equation of the plane, where A, B, C are vectors that are perpendicular to the plane. So this is the general procedure. So not the general procedure, sorry. This is the 3 types of questions that you can get. The first one is you're given 3 points that are on the line. The second type is you're given a point on that plane and also 2 additional vectors that are on that plane. The third one that you can get is a vector that is perpendicular to that plane and 1 point that is present on that plane. So this is, do I have an example? Oh, no, I don't have. Okay, but don't worry. In the video, I have a special video dedicated to chapter 3, part 1 and part 2, where I discuss how do you get the equations. So it's already in the drive. Just make sure you watch the video. So okay, I forgot to ask. So far, are there any questions? Ada pertanyaan nggak sampai sini? Going once, going twice, no questions. Okay. Okay, so for chapter 1 to chapter 3, that's it. I just need to save it and I'll upload it later. Give me a moment. It's still saving. Okay, so I'll stop share. Now I'll share again. Okay, so this is basically chapter 4. The problem is when I looked at your syllabus, the one that I asked for, chapter 4 is also quite a long chapter, but this time I give lots of examples, so I hope this is sufficient. So basically chapter 4 is about general vector spaces. If in the previous chapter we discussed only R2 and R3, in this one we discuss a general, a more broad, a more general type of vector spaces. So basically, let's say we have a general vector space V, and inside V we have non-zero objects. To make it general, we'll call it objects because it can apply to vectors, polynomials, and matrices. So let's say, to make it general, we say objects that are non-zero. And inside that V, those objects can be defined by a summation and a scalar multiplication. Should these two conditions be met, u plus v and k times u, then V is called a vector space. And a vector space must fulfill the following axioms below. Okay. And the next part is a smaller, not smaller, I would say, a much more, I wouldn't say specialized, but a more quote unquote smaller vector space called a subspace. What is a subspace? Let's say just now we have a vector V. Sorry, not a vector V, a space V. Inside here, let's say we have another space called W. So basically W is a subspace of V. A subset, it will be a subset will become part, sorry. To prove that a subset is part of a vector space, then these three conditions must be met. That means 0 must be in A, U plus V must be in A, KV must be in A. If any one of these conditions are not met, that means A is not a subspace of a certain vector space. Okay, so this is what happens. Now let's say here, let's take a look here. Let's say we are given a matrix space. This is called a space or a general matrix space. And we are asked to prove whether A is part of M22. Okay. So the first thing that we should do is prove whether 0 is part of A. And 0 here in this case is 0, 0, 0, 0. And is it in A? Well, yes, if E equals F equals G equals to 0, then that means 0 is in A. Simple enough. And next we are asked to determine whether A1 plus B1 is in A. A1 plus B1 is in A or not. So let's say A1 is this and B1 is this. And it must follow this structure. And so we just have to add the two, separate them, and we get this. Hence, condition 2 is fulfilled. And next one is the third. All you have to do is just multiply A with C. The inside C is F, C, E, C, F, and CG. And we can see that it is here. This is what we get. Hence, all three conditions, as you can see, have been fulfilled. That means A is a subspace of M22. Okay. Okay, next. Now this is another subspace case where V equals to this, where V is a polynomial, and we're asked to prove whether V is a subspace or not. Same procedure applies. Is 0 in U? Yes, it is. If we apply U and V, is U plus V equal to U plus V? Well, as you can see, no, it's not. They're not the same. This and this are not the same. So now we have U, we apply it to the equation, we get this. We have V, we apply it into the polynomial, this is what we get. We add them both, this is what we get. However, if we were to apply U plus V into the system, we're not going to get the same thing. And because they are not the same, hence U is not a subspace. Hence, sorry, not U, sorry. V is not a subspace. Okay. Okay, so next would be another concept called linear combination. And this is quite a simple concept. So basically, if we have a vector W that is in a vector V, a vector space V, okay. So let's say this is a space V and W is in here. Then W should be a combination of the vectors that are in V. So let's say this is V1, V2, V3. Hence, it should be able to be, hence we must be able to express W in this form, where K1, K2, and so on and so forth are called the coefficient of the linear combination. And the next concept is called spanning or rentang, which is also a vector set that is not zero, that is within the vector space V. So if in order to help you understand, we can take a look at these two pictures here. Where, as you can see, span B is the line itself here, and V here, that is determined by V. Okay, I don't really have the right words to explain, but if you look at the diagram, spanning is basically something that follows this order or something that follows this order, that follows the blue. That's the best way I can explain it based on this diagram. And so let's say, so in order to expand spanning, let's say we have two conditions where that S is a set of non-zero vectors that are in V, and W are and subspace W is a subspace that contains all possible linear combinations inside of S. That means we can conclude that W, that all vectors in S means the all vectors in W, in S, all the vectors in S, they span W. Okay. So how do we test if they span or not? We get set S as the matrix coefficient, and then we find the determinant of said matrix. If your determinant is equal to 0, that means it does not span R3, and the vice versa applies. Okay, so this is how we apply. First of all, determine if they are linear combination. So first of all, as usual, we express one of them as a linear combination of the other with the unknown constants a plus b. We have to find the values of a plus b, and which we already have here based on the first and second equation. And then we have to see whether it's consistent or not by applying it into the third equation, this one. If it's consistent, that means we have the solution for A and for B. And this is the linear combination that we have. And automatically, since we determine that they are a linear combination of each other, we can immediately conclude that these vectors, they span R3. As simple as that. And the next concept is what we call linear independence, which is an application of linear combination. There are two ways to determine whether a set is linearly independent or not. So let's say we have this set, and this set is in a vector space V, and S cannot be expressed as a linear combination of the other components, or this is applied, which is the easiest way. This is applied, and we get this in, if this is applied and K1, K2 until KR are all equal to 0, that means all the vectors inside this component S are called linearly independent of each other. Okay, so how do we prove? Let's say we have two different cases, and we're asked to prove whether they are linearly dependent or independent of each other. Now, let's take a look at the first part. So basically, what we're supposed to do is we're supposed to express U1, U2, and U3 as a linear combination of a 0 here. And then we're asked to find the values of K1, K2, and K3. And we can do that by using elementary row operations until we get the reduced row echelon form. And as we can see here, K1, K2, and K3 is equivalent to 0. Okay. Which means they are linearly independent of each other. If we look at the second case to determine whether the polynomials are linearly dependent or independent of each other, we do the exact same procedure as the previous ones. Although, pay attention, the way you treat polynomials, matrices, and vectors are completely different, okay? So make sure you be careful. For polynomials, first you make it into this form as usual. Then you group them based on the coefficients of the constant, x and x squared. And then you transform it into an augmented matrix here. And then, as usual, perform the Gauss-Jordan elimination until you get a final solution that looks like this. Once you receive some, well, you don't have to do a Gauss-Jordan at this case. Well, you can do Gaussian or unfinished Gaussian. If you see the bottom row, it is 0, 0, 0, 0, 0 here. This shows that K3 here has unlimited number of solutions. That is not only 0, but it has solutions that are other than 0. So which means they are linearly dependent on each other. Okay. And sorry if I'm going too fast here because I have like a 2-hour like almost a 2-hour time limit, so I don't want to waste too much of your time. So basically this is next, which is coordinate and basis. So for coordinate and basis, let's say we have this S. S can become a basis of vector space V if they are linearly independent and they span V. If you can prove these two, then we can show that S is a basis of V. And if we have proven that S is a basis of V and the vectors, and let's say we have a vector V and V fulfills this condition, or V can be expressed as a linear combination of the vectors that are in S. Therefore, the scalars C1, C2, C3 until CR, not C4, but CR, are coordinate vectors, or what we call the coordinate V relative to the basis S. So this is how we express it. The coordinate vector, and we can express this as a vector, the C1, C2, C3 until CR. And they are called the coordinate vector V that is relative to S. Okay. And next is an example. So first we're asked to find whether the coordinate vector of V relative to the basis S, V1, V2, and V3. So this is what we do. First, we equate them. We express it as a linear combination of V1, V2, V3. Then we try find the constants A, B, C. And if we already have A, B, C, we will get the VS. And guys, if you don't mind, this one I just use a very simple method of determining it. If you get a much more complex system than this, try not to use this method, okay? Just use the regular Gauss-Jordan elimination until you get ABC. Okay, so this is VS. And the second one, let's say VS is given already, and we are asked to find V. All you have to do is just apply the VS to V1, V2, and V3, like so, and we will get V. Okay. The next one is dimension. Basically, dimension is the number of vectors that are in the basis S in a dimension basically is the number of vectors that are in the basis of a vector space. So let's say, where is it? Back here. We have a basis S. How many vectors are there? 3. Okay, so the dimension is 3. Simple. So basically here we have a common formula for the different types of vector spaces. We have Rn, polynomial, and matrix. So all you have to do is just have a look and then perform the calculations. Okay, now let's say previously here, this one is R3, right? So that means your dimension is 3 previously. Now this one is not that important, you can skip. Now, how do you find the dimension? Let's say you're given a system like this. The usual thing that you should do is convert it into an augmented matrix form and then perform the row operation, the Gauss-Jordan elimination. And here, if you take a look, you have x1, x2, x3, and x4. This one is, that means what's the dimension of this system? Okay, I think I should fix this for a while, because this is a bit incomplete. Give me a moment. Let's say here, you perform the row operations and you see that the leading ones are in x2 and x1. Therefore, x4 and x3 are parameters. And this is what you get in the end. Take a look at x2. So basically, the final equation that you get is x1 plus x3 over 4 equals to 0, and x2 plus x3 over 4 plus x4 equals to 0. Okay, and so since we have already expressed x3 and x4 as a polynomial, not as a polynomial, as a parameter, then we can find what is x1 and x2. Then all we have to do is just x1, x2, x3, and x4. x1 is negative r over 4. x2 is negative r over 4 minus t. x3 is r t. This. So now we express it as r plus t. And since we have two parameters, t and r, your dimension is 2. Okay. Okay, so now next is the change of basis or perubahan basis. Now students, they get confused here because they don't know the legend. This is the legend. You want to have a look. So, and also they get confused because of they don't know exactly what the procedure is. So let's say okay, you're asked to find the how do I say this? You are asked to find the transformation basis. The P. The P is the matrix that changes the old basis to the new basis. So the first thing that we should do, let's say we want to convert an old basis to a new basis. So first thing that we should do is to express the new basis as a linear combination of the old basis. Then you find A, B, C, D, followed by okay. After you find A, B, C, D, we put that aside, and then we take a look at VB, which is the new basis. Okay, so next, step 3, we express V as a linear combination of the vectors that are in the new basis, like this. Like this one here. And then we just input the equation of U1 and U2 into the vectors, and then into this equation. Basically, we put this kenapa sih? We put this into this, which will result in this form. Then we just rearrange it until we get this. And the matrix at 4, don't know what happened to the numbering, the matrix here can be rewritten into this format. And this K1, K2 is this one, which is the new basis. Then from here, we can find the matrices. The matrix P that transforms B acts on the new basis to the old basis. And this is the P. It might seem very, very confusing from here, but if I show you in the example, you're not going to get confused. Don't worry. Okay, so this is just a quick way of finding the change of basis. Just form the matrix, the augmented matrix, use elementary row operation, and then this is what you're going. In order to change the one on the left to become the identity matrix, and then you extract the matrix, this one, from the right side. So this is the simple procedure, and this is also a property that you should know, that the inverse, that the change of basis from old times old to new times the change of basis to new times old is equivalent to the identity matrix. Basically, they are inverses of each other. Okay, so this is the example for part A. First, we take a look at the old basis. So let's say B is the old, B accent is the new. And let's say, first we express, since we want to find B accent to B, let's say the B accent is this one. This is the first step. Express it as a linear combination of B, the old one. I'll just put the numbering so that you can understand the steps. So this is step 1. This is step 2. Solve, find the value of A, B, C, D. Once you have the value of A, B, C, D, this is the answer. And in order to find B, which is this one, all you have to do is just find the inverse of this one. So step 3. However, since we do not have enough time, I'm just going to leave it here. And this is the fast way to find part A. So since we want to find from the since we want to find the new to old, which is B accent to B, all you have to do is just put the bases P1 and P2 on the left and the new one on the right. Then we perform the row operations until we get this as the final result. Until we get this. So basically this is old new. Then we perform, this is the I, and this is P, B accent to B. And hence, this is your answer. It might seem long and confusing, but this is the general procedure. And I've explained it in the best way I can. So I will save this. And I'll reshare again into the, this is our last one. Okay, I'll be very quick with this. Okay, so I don't know whether this is part of the exam or not, but the Wronskian method is part of this chapter. So basically, Wronskian method is used if we have a function, and it can be any function, with the condition that the function, we can perform differentiation on the function using this method. Sorry, not in this method. If the function can be, if it has a derivative in this range. If they are a function, if let's say we have 3 functions, fx, gx, and hx, then the Wronskian matrix will be like this. However, if the Wronskian matrix is not equal to 0, therefore this set fx, gx, and hx are linearly independent of each other. So as seen here. let's say f1x is equals to 1, f2x equals to x, and f3x equals to ex. This is the Wronskian matrix. This is 1, the derivative of 1, a constant is 0 and 0. The first and second derivatives are 0. For x, same thing, and then yeah, this is the same. If we take a look and find this is what we're going to get, the final result, the Wronskian. And this is the final value, the final solution that we're going to get. However, we know that at ex, if you were to draw the graph, ex is never 0 on all values of x. Therefore, since the Wronskian, which means the Wronskian is never 0 for any value of x. Therefore, this given set, f1, f2, and f3, are linearly independent of each other. Okay, so the next concept is the column vector and the row vector. So as the name suggests, row vector are the rows, the column vector are the columns. Okay, should be simple enough. Now this is where it gets the application is what we call the column space, the row space, and the null space. So what is the column space, the row space, and the column space? So basically, the column space is a subspace that spans Rn and so the row space is a subspace that spans Rm. So this might seem very, very abstract, but I'll show you how to find the row space and the column space. And finally, the null space, this one should be the clearest one, is the solution when ax equals to 0. Okay. Okay, ignore that for now. Okay, so how do we find the row space and the column space? So here I present to you two different cases. The first case is that the matrix that you are given is already in echelon form. Then all you have to do is just find the leading ones in terms of the column and the vector. So the leading ones from the perspective of the column, I think I'll just draw it for you to make it simpler. Let's say. Let's say we have this matrix and so on. So this is where the leading ones are. Let's say this is A, B, and this is where the leading ones are. Let's call it row C and row D. Therefore, A and B is your column space, and C and D are your row space. However, if your matrix is not in echelon form, then first of all, you need to convert it to echelon form. Then you can find the leading ones. Okay. So next, how do you find the null space? Easy. So let's say you have a matrix M times N. You treat that matrix into this form. Let's say we have A, B, C, D, E, F. You treat it like this. Then you find the solution. Let's say this is the solution. How many vectors are there? As we can see here, there are 3, right? 1, 2, 3. Therefore, these vector columns A, B, and C consist of your null space. Okay. And the next one is on nullity and rank. So basically, nullity is the number of parameters in the general solution of AX. In here, we can see that there are 3 vectors or parameters in the null space. Hence, the nullity of this system is equivalent to 3. That's the nullity. What is the rank? Well, basically the rank is the common dimension of the row and the column. However, we have this beautiful formula over here to make it simple for us. So basically, in the previous case, we have 3 columns, right? In the previous case. Therefore, your rank is equivalent to 0. Therefore, and we know that the nullity is 3, so therefore, rank plus 3 equals to 3. Cancel, cancel. Rank is 0. Okay, so next, for what if we're dealing with a matrix that is transposed? The rank doesn't change. There. However, your nullity will change. Yeah, so this is just something that you should bear in mind. Okay, so next, these are just some equivalent statements. You can just read through them. And this applies to n times n matrix. This one. For cases of linear systems, we have 2 different cases: overdetermined case and underdetermined case, where this and this applies. You just have to take a look at the augmented matrix. The m times n. Okay. So this is an example of an overdetermined system. It's in your textbook. You can have a look. Okay, so this is an example on how you find the column space, the row space, and the null space. So of this, so let's say you have this system here. The first thing that you should do is to perform Gaussian elimination until you get this form. This is your Gaussian form. Then you identify where the leading ones are. The leading ones are here and here, in the first and second row and the first and second column. Okay. And so the column space are these 2 columns. The row space are these 2 rows. Okay. There, I've written it down for you. And next is to find the null space and also effectively the null, the nullity, and the rank. So basically the null space in order to find the null space, you need to do the Gauss-Jordan elimination. So what you have to do next is convert the row echelon form into the reduced row echelon form. And so this is the reduced row echelon form. As you can see, the leading ones do not change. They're still in x1 and x2. Therefore, x3, x4, and x5 are expressed as parameters as seen here. And so from here, actually, we can stop, but if you want to continue, go ahead. This is your null space. And for the nullity, you have 3. Your nullity is 3 because you have 3 different parameters. And how many columns do you have? 5. So based on that beautiful formula previously, we can determine that the rank is 2. And also, so that's it for the explanation. So I'm sorry if I go a bit too fast for you because we have limited time and we have so much to discuss, but don't worry. For some examples that are not discussed, they are in the Google Drive. I uploaded videos on sample problems. So that's all for tonight. So thank you for coming, and I hope you do well in your